Okay, so we're going to talk now about concepts of finding greatest common divisor and least common multiple, abbreviated GCD and LCM. And there are two kind of methods you should be familiar with. What if you have already prime factorization for the two numbers, of which you're trying to find what the greatest common divisor or least common multiple is. So imagine you have two numbers, right? The one number given is this, and already you have its prime factorization, so you don't really have to multiply it. That's your number. And then you have the other number, the one I'm highlighting in green now, and whose prime factorization is given as well, right? You have 2 to the power 7 times 3 to the power 3 times 5, and the first number you see. Okay, so we want to find the greatest common divisor. So first thing I want to mention that greatest common divisor is a divisor for both. It's a common, right? So divisor for both numbers means it's something smaller that fits in both of those numbers, right? I highlighted. So it's always think of it something smaller. So if you have a prime factorization, you can easily find greatest common divisor. First, common means that you're looking for some common factors. So if I look at common prime factors, so if I look at both numbers, then I see 3 is a common prime factor and 5. Those two show up in both numbers, not 7 and 2. So for sure that's going to be 3 and 5. And now I have to figure out to what powers they need to be raised. Since this has to fit in both numbers, so it's something smaller than both of the numbers, you always go with the smaller of the powers. So in this case, you go with, and let me just maybe remove the highlights here so you see it more clearly. In this case, the common factors are 3 and 5, and you go with the smaller of the powers they appear with. So 3 needs to go with the power 3, not power 5. And 5 goes as 5, so 5 to the power 1, not 5 to the power 7. Because this now divides both numbers, right? Because it's a factor for both numbers, and it's the greatest common factor. So of course this one, let's say we can multiply, it's 27 times 5, so 135. I wrote here, leave your answer in the exponential form. So to me, you can leave the answer as such, especially if it's going to involve very big powers. Then there's no point for me to calculate it, because then you would have to just plug it into calculator. And I just want to know that you understand the process, okay? So let's do a similar example, just different numbers. Greatest common divisor for the two numbers given. The first number has prime factorization 3 squared times 5 to the power 4 times 7 squared. The other 2 to the power 4 times 3 cubed times 5. So the common factors here again are 3 and 5. And you go with the smaller of the powers, so 3 squared and 5. So 45. Okay, so you select common prime factors showing up in both numbers. So let me give you some other example, just so because we again had something else than what we did. Let's say 2 to the power 5 times 5 to the power 7 times 7 times 11 to the power 5th. And the other number will be 2 to the power 3 times 11 to the power 9 times 13. Okay, so if you look at those two numbers, the two common factors are 2 and 11. They show up in both factorization. So that's going to be, and you choose the smaller of the two powers. So that's going to be this. And I'm going to leave it as such, because 11 to the power 5 is a very big number. All right. So let's look at the least common multiple. So least common multiple, on the other hand, looking at the number that both of those numbers can fit in. So least common multiple is something bigger now than both of the numbers involved. And both of the numbers involved should be factors of that number. and we're looking at the least common multiple, right, of the two numbers. Okay, so how does prime factorization help? That in fact, if you're talking about least common multiple, you're gonna list all the prime bases you see in both numbers. So we're not going for common, you list them all. So I see 2, I see 3, I see 5, I see 7. Notice even though 2 and 7 were not common factors, but they will have to play a role with the multiple, okay? Because we now want to make sure that both of those numbers will fit in this number we're creating. So that's why 7 had to participate, and 3 also even, and 2 as well. So basically you list all the prime bases you see. I see 2, I see 3, right? Actually in both. I see 5 and I see 7. You list them all. Now what powers you go with? Well, 2 only appears with power 7, so that's the power it goes to. 3 appears as 3 cubed, and 3 to the power 5th, so you go with the bigger of the two powers. Because remember, both 3 to the power 5th and 3 cubed need to fit in that number, so you have to go with the bigger power. 5, well, 5 bigger appears as 5, and then 5 to the power 7, you go with the bigger of the powers. And then 7 just appears as 7 squared, right? So that's the power you go with, right? So since I only had 7 squared, I didn't have the lemma here, it's just 7 squared. When you have two different powers, then you go with the bigger power. And that's the answer. So let's look at this one. I see 2, I see 3, I see 5, and I see 7. 2 is to the power 4. 3, I have 2 powers I can choose from, 3 squared or 3 cubed. You go with the bigger. 5, again, you go with the bigger. And 7 is just 7 squared. And you have it. Alright, so now we're going to talk about greatest common denominator. Okay, so this, guys, when you don't have prime factorizations of the numbers, of course, one way would be, okay, how about I find what's the prime factorization of the two numbers? But sometimes the numbers involved would be very big. So finding prime factorization could really be too time consuming. There's a quicker method here. And this method is just about called Euclidean method. I'm going to leave the room there. And I'll explain that method while we go. You probably remember from our lectures. But the idea is that you, when you look at the two numbers, you're gonna, this greatest common divisor will be the same as greatest common divisor, and you, of the smaller of the two numbers, which is this, and then the remainder of dividing the bigger by the smaller. Okay, so let's think about what did I say? So I need to find the remainder now. So I rewrote the smaller of the two numbers, this. But then the second number in this greatest common divisor equation is the remainder. What is the remainder when we divide bigger number, there's 3,415 by this. So to know the remainder, you kind of have to know how many times this fits into the number, and then subtract, take away that many of those. It's the biggest possible multiple of 3,075 from that number. But so anyway, but here we see that 3,075 fits only once, right? So quotient is 1, because this goes once into 3415, right? So what's the remainder from that number? Subtract this 1 one multiple, so subtract 3075, right? And you can do it on the calculator and you're gonna get 340, right? Okay, so this is the second number it goes to. And then you repeat this process until you're dealing with something you know. And when, by the way, you stop it, if you already see that one of the numbers is a divisor of the other, then this number is going to be the greatest common divisor, because that number then would be the biggest number dividing both, right? So if the smaller number is already a divisor of the bigger number, then the process stops, because that then is the greatest common divisor. So let's repeat this. So that's, I'm going to write, was 1, right? That now it's number 2. I'm looking at now dividing 3075 by 340, and I need to know the quotient to figure out the remainder. So first you can grab a calculator and just do this division. What's 3075 divided by, and I'm gonna do it by 340. When I typed it on a calculator, I got 9.04. So what that tells me that it fits fully 9 times. That's my quotient. And then you have to do on the calculator. So what is 9 times 340? So do that on the calculator. 9 times 340. Well, that's 3060. So quotient is 9. So then that means if you subtract from the number 9 times 340, you're gonna left with the remainder 15. So that's the quotient, that's the remainder, right? So first you figure it out by just doing this division, that when you divide 3075 by 340, it's 9.04. That means 340 goes 9 times into 3075. 9 times 340 is 3060. So when you take it away from 3075, you're left with your remainder 15, right? So this means, continuing, that this is now greatest common divisor. Again, this you keep the smaller of the two numbers and then the remainder, right, of their division. Okay, so then you do, this was the second. Now we continue this until it's obvious for you what's going on. So now the two numbers involved is 340 and 15, right? We're here. So let's do what's 340 divided by 15. Just grab a calculator. That's about 22.6. So 22 is my quotient. So now what is 22 times 15? It's 330. So when I take from 340 22 times 15, so when I take away 330, I'll get my remainder. Right? So I need to know the quotient. Once I know how many times 15 fits into 340, that 22 15s need to be subtracted from 340 to see what's the remainder. So remainder is 10. Greatest common divisor of 15 and 10. Okay, and then you repeat this process. Here I don't need calculations because I see that 10 fits once into 15, and what's the remainder is 5. So again, I rewrite the smaller number and then the remainder, because when you fit 10 into 15 once, what's left out is 5. So now I see that actually 5 is already a divisor of 10, so that's the greatest common divisor, because 5 divides itself and also divides the 10. Okay, so let's look at the next example, just to practice that. Again, we're going to go through Euclidean algorithm. So grab your calculator and try to do it alongside with me. Notice how big numbers are. So this would be very tricky to find prime factorizations for numbers. So Euclidean algorithm is definitely the way to go. So first I'm gonna, this is 12,924 divided by 11,637. So I see the quotient will be 1, right? Because obviously 11,000 will fit only once into 12,000. So so it only fits one time, so only one time this number needs to be subtracted from the original number, and that's going to give me my remainder, right? So that's going to be 1,287. You can do it on the calculator. So that's the remainder. Okay, so that means this is the same as greatest common divisor. I keep the smaller number and the remainder. So then you repeat the Euclidean algorithm. Now you need to do the division of 11,637 by 1,287. You can do it on the calculator, just see what that gives you, to see what's the quotient. 637 divided by 1287. I got this about 9.04, so I know that quotient is 9. So now from the bigger number, I need to subtract 9 times 1,287 to see what's the remainder, right? So I do that. And I got the remainder to be 54. Okay, so now that's the same as, that's the remainder. So continuing this, I keep the smaller number and then the remainder 54. So now you continue this Euclidean algorithm. Now the two numbers involved are 1,287 and 54. So do this division to see how many times, what's your quotient. So when you divide on the calculator, you get about 23.8. So this is your quotient, 23. So now to get the remainder from 1,287, subtract 23 times 54. So first you multiply by 2354 and then you subtract it from that and you get the remainder to be 45. So now that's the greatest common divisor of 54 because you keep the smaller number and the remainder. Now I see that this one will not require any calculation because I see 45 goes only once into 54. And the remainder will be 9, right? So again, I rewrite, keep the smaller number, 45, and the remainder. And now 9 is a divisor of 45, which means that 9 is now the greatest common divisor. So when you end up again with already something that's the divisor of the bigger number, that's the greatest common divisor. And that's the procedure. Now D part is tricky. If you know what's going on, it's not really difficult. Here it relies on the fact that the greatest common divisor of two consecutive numbers, so one apart, is 1. Why? Because the greatest common divisor, I'm gonna take those two numbers. If you just did one step of Euclidean algorithm, so you would keep the smaller number, and what's that? This number fits only once into the bigger number, and they're 1 apart, so that when you take that subtract that from the bigger number, the remainder is 1. And since 1 is already a divisor of the bigger number, the greatest common divisor is 1. So you didn't have to do this step because we know that the greatest common divisor of two consecutive numbers, so when they're just one apart, must be 1 because the remainder then is 1. And so Euclidean algorithm leads to that conclusion. Okay, so greatest common divisor is 1. And when you have three numbers, the greatest common divisor of the three numbers, it's greatest common divisor of the two numbers of your choice, and I chose those, so of 1 and this, right? Let me organize from the bigger number first. Right, this was greatest common divisor of the other two numbers, and that must be again 1 because 1 is already the divisor of the bigger number, so that's the greatest common divisor. So if you, regardless how many numbers you have involved in this string, if the two numbers there are consecutive numbers, meaning they're 1 apart, that will make the greatest common divisor of all this triple to be 1. Because the greatest common divisor for the pair that is 1 apart is 1. Okay, so that summarizes this. Let's look at the next problem. Number 13 is going to talk about the idea of how do we verify if something is prime or not. Well, there's a simple sort of recipe. Sometimes it's tricky to see if the number is prime, but it turns out that we only have to check the divisors up to the square root of that number. So here it should be 347. What numbers must be checked as potential divisors of 347 in order to determine if 347 is prime? Okay. Alright, so what we do? We first take square root of 347. So you take square root of that, and that's about 18.6. So we had this theorem that told us that we only have to check divisors or all prime divisors up to 18. And what are prime numbers up to 18? We have the list right there, so we can list them that it's what 2, 3, 5, 7, 11, 13 and 17. Those are all prime numbers. Again, you have the list up to 18, all prime numbers. So if this number 347 has any divisors, it must be among those numbers. Okay, so that answers what numbers must be checked as potential divisors. Well, those I listed, right? 2, 3, 5, 7, 11, 13, and 17. So now let's check them. So basically you can grab a calculator and say, I'm going to rewrite those numbers. Sometimes calculator, sometimes just our assessment is enough. Number clearly is not divisible by 2, it's not even. To be divisible by 3, the sum of digits has to be divisible by 3, and the sum of digits is 3 plus 4 plus 7 is 14. It's clearly not divisible by 5. By 7, I don't know. We don't have easy tests, so you can grab a calculator, divide by 7, and you would see it's not divisible by 7. Now, you can also check a calculator. Is it divisible by 11? No, you're going to get 31.5. So not a whole number. Is it divisible by 13? Again, you can check, grab a calculator, check it, no. And finally, is it divisible by 17? No. Which means that, yes, 347 is prime. Because all the list of potential divisors, I was able to kind of eliminate each. None of those numbers are divisors of 347, which means the number has no divisors, other of course than 1 and the 347. Okay, so simple as that. Let's look at the next. I'm not going to do more than 2 examples here, and there's a mistake here. What numbers must be checked as potential divisors of 611 in order to determine if this number 611 is prime? So for the first, I need to determine what square root of 611, right? So I look at square root of 611, that's about 24.7. So potential divisors are all prime numbers up to 24. So 2, 3, 5, 7, 11, 13, 17, 19, and 23. Again, look at the beginning of the exam. You're going to have the list of prime numbers up to 100. So you can just use the list given. Okay, so let's just one by one, you grab a calculator, or in some case you can just assess by looking at the number. If it's not divisible by 2, it's not divisible by 3 because sum of digits is 8, not divisible by 5 because last digit would have to be 0 or 5. It's now is it divisible by 7? You can check no. Is it divisible by 11? We have a test for that, or you can use a calculator. The test would be 6 plus 1 is 7. Subtract the remaining sum, that's not divisible by 11, so no. Or you just use a calculator and do 611 divided by 11. Is it divisible by 13? Again, use a calculator. 611 divided by 13. I'm going to do it right now, and yes, it is. 611 divided by 13 is 47. So is this number prime? No. 13 divides the number. So this number is not a prime number. Okay, so how many divisors what's the best way to list all the divisors of the given numbers, making sure we didn't forget any? Okay, so for number 34, maybe even without the method I'm going to show you, you could be able to do it, but the method I will show you is kind of like this kind of recipe that ensures that you're not going to just miss on one divisor accidentally. Okay, if you just follow it, you're going to for sure list all potential divisors. And this method relies on having a prime factorization for the number. So 34 is what? 2 times 17, right? Okay, so you have prime factorization of the numbers 2, and then the other is 17. That's a very nice one. So you create a table. You start with 2 to the power 0, which is 1, and you climb up to the power that 2 appears with. And here both 2 and 17 just appear with power 1, so there's no much climbing you have to do. Okay, and then the other here, I'm going to list in column. Again, 17 to the power 0, that's 1. And 17 to the power 1 is 17, and you stop there. You don't increase the power because 17 in the prime factorization ended up with power 1. So then you do all possible products. So this is 1 with 1 here. That's 1 with 2. 17 with 1. And 17 with 2. Okay, so those are all possible divisors. And number of divisors, maybe let's start with that, always follows this formula that you increase this power of each power by 1. So 1 plus 1 is 2. 1 plus 1 is 2. So you must have the total 4 divisors, and this B allows you to list all the divisors. So divisors is 1, 2, 17, and 34. Okay, but that was simple one, because without even knowing this, you should be able to figure that out. Let's look at something else. Let's look at 200. 200 is has prime factorization 2 to the power 3 times 5 squared, 8 times 25. Alright, that's that. So how many divisors have? Number of divisors. Look at the powers. It's 3 and 2. So you multiply 4 times 3. You increase by 1, right? So 3 plus 1 will be 4. 2 plus 1 will be 3. And what's their product? 12. Okay, so you know you have 12 divisors. So now you can just list all the divisors that come to your mind. And you know you have to list all 12. But I'm going to show you the method that allows you to not to think much, to just come up with the divisors automatically. So notice I have 2 to the power 3. I start with 2 to the power 0, then 2 to the power 1. I don't stop. I have climb all the way to the power 3, 2 to the power 2, and 2 to the power 3, that's 8. Okay. Now 5, I start with 5 to the power 0, then 5 to the power 1, and then 5 to the power 2, and I stop there because the power of 5 at most goes, in my prime factorization is 5 squared. And then do all those possible products. That's 1 times 1, this is 1 times 2, 1 times 4, 1 times 8. So far I have 1, 2, 4, and 8 as my divisors. Then here's 5 times 1, 5 times 2, 5 times 4, and 5 times 8. So that's 5. Then that's 10, 20, and 40. Those are another 4 divisors. And then last row is 25 times 1, 25 times 2, 25 times 4. Sorry, 25 times 2 is 50, what I'm doing, 50. This is 100. And 25 times 8 is 200. So now you have the next 4 divisors, 25, 50, 100, and 200. So you can list all the divisors. 1, 2, 4, 8. And you can organize them from the highest to the lowest. 1, 2, 4, 8, there is a 5 earlier before 8. Then 10, 20, 25, 40, 50, 100, and 200. I organized them from the smallest to the highest value. You didn't have to. You could have just listed 1, 2, 4, 8, 5, 10, 20, 40, 25, 50, 100, and 200. Those are all 12 divisors, right?